Good morning, good evening, or good afternoon, wherever you are. And I'm going to give a course, a 4-lecture course, a mini course, about quantum groups and Hopf Algebras. So I think this is a great opportunity to learn some facts about quantum groups and algebraic quantum groups and the structures and examples and things like that. The idea is to introduce the concepts and ideas from an intuitive point of view, but also with examples. So the first two lectures, we're going to see some ideas and the classical picture. And in the last two, we're going to see examples, and we're going to make a lot of computations, which is natural in this subject, okay? So if you have any questions or comments or whatever you want, you can stop me and ask, okay? You're free to ask whatever question you have. And okay, that's it. So it's a great opportunity to learn something about quantum groups. So I hope you take advantage of that. And the people maybe if you're looking at this as a recording, and you can stop me whenever you want, but you cannot ask questions. So I will start by saying that I will dedicate this first lecture to Pierre Cartier. Pierre Cartier was a member of the Bourbaki group, and he was at the very beginning of quantum groups and Hopf Algebras. He did a lot in the theory, and today we're going to see two theorems due to him and other people. So he passed away last August. Oh, maybe I was once with him in Cordoba in Argentina, but maybe he didn't remember me. But never mind. I want to dedicate this first lecture to him. So, what is the course about? The course will be about the relation in mathematics between these three theories: geometry, algebra, and categories. Okay? As in the very beginning of mathematics, all ideas come from geometry. Okay? With geometry, you describe the world using graphical ideas, and then humanity was able to traduce all the geometry into algebra. Today we're going to see this dictionary between geometry and algebra. And what do I mean by that? The idea is we have the same theorems, the same facts, but described differently in the side of the geometry and in the side of algebra. And as we are going forward in the lectures, we are going to see the relation with categories, which is the modern language for quantum groups. So if you go to a congress or a meeting of quantum groups or something related to that, you will hear the word Hopf Algebras, or non-commutative geometry, or tensor categories, or any combination of these three. So these are all related, and more or less, they are describing the same things. But of course, if you want to be precise, then you have to talk in one language, in algebra and categories, or in geometry. So let's start with the classical setting, okay? All the ideas come from the classical setting. So let's do a diagrammatic approach of that. So first of all, I will fix a field. The field could be any field. At some point, the field would be the field of complex numbers, but actually, the theory works for any field. If you want to do analysis, you work with the field of real numbers. And if you want to do some algebraic groups in finite characteristic, then you work with the finite fields. I will work mainly with the complex numbers. So, as I said before, we have the first lecture is about the relation between geometry and algebra. Yes? So let's take a geometric object, say a set, any set. Could be a finite set, an algebraic set, which is given by zero of polynomials, or a topological set, and whatever. Then this is a set with certain properties. But to study this set in geometry, we do the following. We go to this algebra side, to the algebraic side, and consider the functions on the set. This philosophy is an old way of thinking, and it was used a lot by Grothendieck, that said one should study the functions on something and not the something itself. So what is that thing, the thing of functions? So if you're considering a finite set, just consider the functions from the set x, from the set x to k. If you're considering algebraic sets, then you look at rational functions, which are polynomial functions in some way. We will show you a lot of examples about that. If you're considering topological sets, then you consider continuous functions. So these functions, as we know from the very beginning of our career, are an algebra. What is an algebra? It is a vector space with a multiplication which is bilinear. What do I mean by that? Okay. And the idea is we take two functions and we multiply them like this. And what is the multiplication of two functions on an element is just the pointwise multiplication. Of course, in the vector space structure is the sum of two functions is just the pointwise function, sum, sorry. And the multiplication by a scalar is the same. We just multiply by a scalar the value of the function. So with this thing, this is an algebra. And this multiplication has to be associative. And in this case, it's very clear that it's associative. Associative means that if we multiply three functions like this, then we have this equality, as everyone knows, okay? And of course, the definition of the multiplication is given here in this row. There is another way to write the associativity here, is using diagrams. For example, the multiplication is a map that goes from, no, I don't have enough space. Let me write A instead of X, so I have more space. The multiplication is a map going from the tensor product of the set by itself to one copy. Why the tensor product? Because it is a bilinear map. Okay? The bilinear map goes from A times A to A. So this is the very definition of the very well-known property of the tensor product. Every time we have a bilinear map, we can consider this thing as a linear map from the tensor product to A. So this is a multiplication. So the associative axiom, the associativity axiom, means that if we multiply first, let me put with colors. In the first two legs of the tensor, so f tensor G, tensor H goes to F tensor F times G tensor H. Or we may go the other way around and multiply first the two G and H, and then we multiply again, and we get the multiplication F times G times H. And we go in this way, we multiply and we get FG times H. So the associativity means that this diagram has to commute. This is the way of understanding that something is associative by diagrams. So what is the idea in category theory is to forget about elements and look at the diagram itself. So we look at this diagram, and that it is commutative means that if we go one way, I should get the same result if I go in the other way, if I use the other path. So that's the nice idea, because we forget about elements. Nevertheless, when working with quantum groups or with algebras, we will use a lot of elements at the very beginning, so don't worry. I will take my time to introduce you diagrams. Yes? Okay. So, moreover, when we define the multiplication, and these are numbers, this is the same as writing gx times fx. You know, because they're numbers and their numbers commute. So this means that the algebra is commutative. So how do we write in diagrams that it is commutative? In diagrams is we have two copies of the algebra and then we multiply, or first we twist the elements, and then we multiply. So in elements is we take F, G, and multiply, and we get F times G. Or we twist, we call tau this twist map, or the flip. We twist, we change the order of the tensors, and then we multiply, and we should get the same. Yes? So, in diagrams, the commutativity looks like this. So, I'm saying, like, if you have, okay, I will tell you tomorrow about this, but if you have and something like an object with these properties in any category, with sufficient properties, then you can say what is associative and what is to be commutative. So from the very beginning we have a set, nothing but a set, and then on the side of the algebra we have an object with a lot of properties. So you see why we are changing from a set to the algebra, because we can try to understand the geometrical set by starting the algebra. So what about functions? What about if we have, so I'd say we have to understand functions on the geometry, on the sets, and not the sets themselves. So what about if we take a function between two sets? So let's take a function between two sets, between a set x and a set y. As usual, if they are finite sets, you take any function. If they are algebraic sets, then you take rational functions. And if the sets are topological sets, then you take continuous functions, and so on and so on. If we look at the other side, what happened with the function algebras, then we see that we have a map, but in the other direction. Or what is, so let me show you what is going on. So if we have a map from X to Y, let's call it F, then what happens when we think about the functions on the algebra? If you take, I will put F everywhere, so maybe I will write the functions here like alpha. If we take an alpha here, then the alpha is a map from Y to the field. Yeah? Could be any field. And if we have a function here, then this defines a function that we call F star of dual F, or the transpose of F. And it's defined just by composing the things. What do I mean? We have our map, alpha, and the idea is, okay, I pre-compose with our F. So this gives us a map from X to K. This is just the composition. And this is what I call F star of alpha. Yes? So in an element, F star of alpha in an element X is just alpha of F of X. So what I'm saying is, if we have a map between two sets, X and Y, when we look at the algebra side, then the maps are going in the other direction. But that's okay, we still have a map relating these two things. Okay? So, maybe it's too complicated or too abstract or too general to understand a thing, so let's look at an example. Okay, before looking at an example, I wanted to say another thing more. We can go back from the algebra to the geometric side. How do we do that? We take the spectrum. The spectrum, in this lecture, we have a lot of definition of a spectrum, but to be concise, the spectrum for us, say we are working on the complex numbers, would be all the algebra maps from our algebra to the field. So this is called the spectrum. Okay? For any commutative algebra, one can define the spectrum. In algebraic geometry, we have different definitions, but we stay with this one. Okay? So let's look at an example. Take one of the very easiest algebra. Actually, when we have the complex numbers, these are the simple algebras. It's a very simple algebra, the matrices. This is the ones that we learn from kindergarten how to play with in the very first course of mathematics. Yeah, the matrices. We know that the matrices, we can sum matrices, multiply the matrices by a number, and if we have the correct size, then we can multiply them. So these are an algebra. Okay, this is an algebra. But this is also a set. Okay. So if we take this set as a set, just a set, then we consider the functions on this set. So the functions that I'm going to take is the polynomial function in Y, well, because we consider this set as an algebraic set. So these are polynomials, just polynomials in n squared variables. Yeah? Note that polynomials are not all the functions on the matrices, because I'm taking all the polynomials. Yeah? So, as you see in the polynomials, here, they are spanned by the variables, n squared variables that I denote this xij. Yeah, there. So how does it define a map? Okay, you give me a matrix, and then the xij variable applied to a matrix gives you the coefficients in the ij entry. So this is called, in general, the matrix coefficient. So you take a matrix that the functions xij gives you the ij coefficient. Okay, very simple. given any matrix, we can have the coefficients. And actually, these variables are not just given, they are not coming out of the blue or just by inspiration. They are just the corresponding dual basis of the elementary basis of the matrices. The EIJs. The EIJs are the matrices which has a 1 on the I row and the J on the J column. These ones. So these Xij are just the dual basis of that. Okay, and the algebraic functions on the matrices is the algebra of regular functions. Yeah? This is what we call in algebraic geometry the algebra of regular functions on the matrices. So how do we go back? So suppose that we have the polynomial. So the picture is matrices is a very nice object. The function on the matrices is a very nice object, polynomial algebra, in a lot of variables, but as many variables as the size of the matrix. But still, a polynomial algebra. And how do we go back? So we have the polynomial algebra. So as I said before, we have a way back to the sets, which is taking the spectrum. So let's take the spectrum of our polynomial ring, which is the spectrum, okay, all the algebra maps from the polynomials to the field. Okay, what is that? Don't worry, it's very easy. So if we want to define a map on the polynomials, we have to say just the values on each variable, okay? Because, why? Because it is an algebra map. This is why being an algebra map is easier. Yeah? For example, if we have a polynomial like this, and we want to define a map, He, on this, and as this should be an algebra map, then first it divides is additive, so we can divide the sum, and then it behaves very well with respect to the multiplication, so we have this thing. So, for example, this is an example, but this works in general. So to define an algebra map on the polynomials, we have to say only what is the value for xi, for any xij. And okay, so with that we can build a matrix, the matrix given by the xij's. So in this case we have 2 by 2, so we have our xi is xi of x11, xi of x12, xi of x21, and xi of x22. That's it. So given any algebra map, we build a matrix. Conversely, given a matrix, we define an algebra map. How? This way. You give me just this value, so with these values, I said, okay, the values in the variables are just the ones given by the matrix. So this means that any algebra map from the polynomials to the field is given by a matrix, and any matrix defines an algebra map. So we are saying that the spectrum of the polynomial ring of our functions on the matrices are just the matrices. So we have, what have we proved? That the operations that we define are reversible. So we have an equivalence. Yeah? We go back to the same object. And I will show you today that this is a big theorem, okay? So, up to now, the idea is we have two theories in mathematics. I describe the things with the algebraic setting. Given a geometric, maybe it's the way this side, because I'm the other way around. Given a geometric object, we constructed an algebraic object given by the functions. But we can go back and obtain to the same place where we left. Yeah? So we have a dictionary back and forth from geometry to algebra. And this works every time we have a commutative algebra. So, are any questions so far? It's maybe too general or too abstract. But you can stop me whenever you want, okay? So let's start putting some ingredients in our dictionary. Maybe someone in the chat. So the first question, the slides, yes, I will upload them in my personal webpage, but this thing, the video of this course will be uploaded somewhere else in the webpage of the CIMPA and the ICTP. And the idea is why the rows are reversed in the algebra case. The rows are reversed in the algebra case because it's the easiest way to compose the things. Yep. So if we have the map F gives you a way to relate any map from Y to K to a map from X to K. In the other way around, it's not so natural. Okay? If you give me this map and I have a map from X to Y, then by composing, I have a map from X to K. So this is the way. There are other reasons, but this is the easiest way to explain that. It's the natural way of composing things. Yeah? In general, this works like this. When you go to the functions place, then everything is reverted. It's like a mirror, yeah? But it's just a mirror. Okay. Do we have more questions or no? Let's put some ingredients, some spicy things, not so spicy. Let's assume that our set from the very beginning is a group. All right? What is a group? So we take a finite group, an algebraic group, a compact group, or a differential group, as whatever you want. The example is going to be about finite or algebraic groups, okay? But this theory has a lot of incarnations in all possible domains, say. Because in analysis, this is called with another name. Yeah? Okay. Now it's working. A group. What is a group? We have a group is a set with a multiplication, and the multiplication is associative. So come with me, and the multiplication is change the screen. So I will cheat, and I will write the associativity. Now, okay, let me erase this thing, but it's the same. The associativity of a group is, I will erase everything. So, the associativity of a group can be written like this in terms of diagrams, yes, as I showed you before. So you see the equations in the slide, and to reproduce these equations in terms of diagrams, I will write something like this. So first we multiply the first two, and then the second one we leave it. So we are doing something like this: G, H, K. We first multiply the first two, G, H, K. And then we multiply these two, and we have this element, which is on the left-hand side in our slide. Or we go the other way, and we multiply first the last two coordinates of the element. So we have this pair now, and if we multiply them, we have this result. So the associativity is asking for these two things to be equal. So this means that this is a commutative diagram. So this is the associativity, and we have a unit. And for the unit, we have, as we know, we have a unit that when you multiply any things by the unit, you do nothing. Yes. So how do we interpret the unit as diagrams? So the unit is, okay, it means that the unit, the axiom is we have one distinguished element that has this property. So to say that we have one distinguished element is we have a map from the set with one element, E, to our set G, our group, that we'll call it U. And to be a unit, it should satisfy that equation, this equation. So I'm changing too fast the equation of the product, so I will write it here so you don't change the screen. So how do we write this in our terms? Okay, the idea is, okay, we have if the thing is, first we multiply by our distinguished element on the left. So if we do our map, the unit times the identity, then suppose that I will write them with the elements. What I'm doing is we have the pair of coordinates EG that goes to this pair EG, but now it means that this E, I'm doing something very wrong, but I'm using the notation that the image of E is E, okay? I'm not writing U of E, because maybe it's too much. So, and with this thing, then we multiply. And if we multiply these two things, we get EG. Yeah? So we do the same on the other side. And which is that identity times U. And we multiply, and we get GE. And these two things should be the same, and they should be the same as E. So the idea is, as sets, these two things are the same, G times 1. G, the coordinate product, the Cartesian product between a set and a set with one element is the same as the set with one element, okay? You just forget the first one because it's only one. So these are, it's not like the identity, it's like they are bijection, okay, as sets. And they should be the same. Yes? So this is the diagrammatic way of thinking about the identity. As you see, it seems to be more complicated than the associativity. But it is what it is, okay? So the identity is another property for having a group. If we don't have the identity, then we have another thing. Yeah? It's not a group. Semigroup. All right, up to now, these are the definitions for a monoid. If you recall your course in algebra, this is a monoid, and we have one map that is distinguished. The thing is a group if we have an inverse. Yes? So I will write the map for the inverse in a couple of minutes. Well, I'm not doing this now because I want to see what is going on the algebra side for this map. So as I said before, if we have a map going to one direction, then in the algebra side we have a map going to the other direction. Yes? So if the multiplication is going from, now change to our slide. If the multiplication is going from G times G to G, then on the other side we get the transpose map or the dual map going from the functions on G to the functions on G times G. Okay, what is that? Exercise. This is the tensor product of these two. And it is co-associative. Or what does co-associative means? Okay, let's go to the blackboard. Co-associativity is, this is associativity. But if we change to the algebraics, to the algebra side, to the functions, then we have to change everything. All the arrows have to go in the other direction. So we do that. Let's put in no, I don't know, green. If we go to the algebraic side, so let's erase the elements. So if we go to the other side, if we check the O's, so what was times becomes tensor. And what all the maps are replaced by their duals, and I forgot to write here the multiplication, and the arrows has to be inverted. So co-associative means that this diagram commutes. So it's a dual diagram of the other. The arrows go in the opposite way. So the question, the very first question was why the arrows are inverted in the algebra setting. So it's very deep because here all the arrows are inverted. So we have another notion which is dual from the first one, which is the associativity. Now is translated into something that is called co-associativity. It might be weird, this thing, but actually it's better than the other one. I will explain you during these 4 lessons why. Okay, so this is co-associative. We do the same with the unit. So if we have a unit in the group, then we look in the algebra side, and the arrows go the other way around. So if the other arrows go the other way around, we have a map from the functions. So we have a map from our functions to our functions on one element, and the functions on one element is just the field. So this is a transpose or the dual of the unit. So what is the axiom of the property that the this dual should satisfy the same one of the unit, but we have to reverse the arrows. So change the objects and reverse the arrows. So let's do that. Where is G? We put O of G. And where is times? We put tensor. And where is the E? We put the field. Put stars everywhere. Not with identity because it's the same. So we put here K. So this is a co-unit. And I forgot to put the arrows in the other direction. Of course, you can do it by hand, but if we try to leave the elements behind, we will have the idea faster of what is going on. We just, when considering functions, we think the properties as diagrams going in the other direction. So this strange diagram is saying that what we have is something like a unit, this is called co-unit, and we have co-associative. So this is, the idea is with the co-multiplication, you take two objects and the answer is one object. But with the co-multiplication, you take one object and we split in two. So we write something like this. In some books, you will find something like this, because something in the tensor product is sum of elementary tensors, something like this. But I will use like the Heinemann notations and Sweetler, so I will not write the sum, but just this thing. Yeah. So this is called the Sweetler notation. Okay. And the same happened with the inverse. Yes. We have another map that is called the antipode. Okay, so as you see, even for a group, the very beginning of a group theory, if you look at the functions, you have like a new object, which has this strange property. The map here from itself to the tensor product of itself, something that is called the co-unit, and something that is called the antipode. So this map is called the coproduct because it's the opposite way of the product. So okay, we look only at these properties and then we do a definition. So the definition is just, we put, there is a typo up there. There should be a coalgebra, not a coalgebra. Sorry for that. So a coalgebra is a triple, so a vector space with a co-multiplication and a co-unit. These maps are linear and they satisfy the co-associativity and the co-unit. And you see, what is on the slide is exactly what turns out to be in the blackboard. Yeah? So it's not abstract nonsense of why to define coalgebras like this. They are natural when we are considering functions on groups. So we have a coalgebra structure. The dual space of a coalgebra is an algebra. Okay? So for the first question that was why in the algebra setting the arrows are inverted. The way to think about that is think about the dual vector space of a vector space. When you have a function between two vector spaces, then when you think about the dual, then the function goes the other way around, and the matrix is the transpose. So this is here is the same. So when you think about the coalgebras, we are thinking about dual of algebras. And the dual of a coalgebra is always an algebra, but the dual of an algebra is not always a coalgebra because we have a problem. Yeah? And we will see the problem later on. But the dual of a coalgebra is an algebra. Yeah? Always. So, when we mix these two structures together, we have what is called a bialgebra. What does it mean to mix the two objects together? We have an algebra, so we have a vector space with a multiplication and a unit. We have a coalgebra, the same vector space, with a co-multiplication and a co-unit, anyway. And if these two structures are compatible, then we have a bialgebra. What does it mean to be compatible? That one structure is preserved by the other. Miracle or no? Just math. If one structure is preserved by the other, the same happens with the other structure preserved by the first one. It is a very nice exercise about diagrams, so I recommend you to do it, okay? So, in diagrams, so I'm going slowly out of elements and looking at diagrams. So the first diagram is that the co-multiplication is an algebra map. Yes? We have two copies of our algebra. If we multiply, we get an algebra. We get the B, one copy of our algebra. And if we could multiply, we get two copies of our algebra again. But we can do the following. We could multiply on the first tensor and we get two copies. Or we could multiply on the second tensor and we get two other copies. Then we have to multiply these two copies with these two copies. For doing that, we do it tensor by tensor. So the diagrammatic way is we interchange the tensor in the middle with this doing this map, the identity here, and the flip in the middle, and then we'll multiply. If we get the same result by going this way or this way, then the co-multiplication is multiplicative. Yeah? And the same with this one. And of course, it means that also the co-multiplication of the unit is 1, tensor 1. And this is for the co-unit, yes? So, saying that the multiplication and the unit are coalgebra maps are the same diagrams. So, the same diagrams indeed, yeah? So you have to think about it a little while, and then you will have you will be illuminated and say, it's the same diagram. Yes, it's the same diagram. And our first example was the bialgebra. So now let me give, okay, there's a question. Okay, the flip. I will write you the flip. Why the flip? The idea is come back to the blackboard. The idea is, how do you multiply 4 copies of things? So I will put the brackets now here, so you see what I'm trying to do. Yes? This is the algebraic structure of the tensor product of an algebra. So you take, or let's do it in elementary tensor. We want to multiply these two tensors. How do we do it naturally? Naturally, say the first one with the first one, the second one with the second one. Yes? So you see A, C, tensor, B, D. And this is the natural structure of a multiplication of two things. The first one with the first one, the second with the second. And to do that, the idea is you have to go, C has to go from here to here, and then we multiply. So the idea is we interchange first the things in the middle and then multiply. So if we interchange the things in the middle, then we have the idea of how do we do that? Just now we multiply. We apply the multiplication here and the multiplication here. And then we have our map. This is why we apply the flip. Because we want this structure. First one with first one, second with the second. And for that, we need to flip the things in the middle. Okay, so let's, before going to a break, I'm 5 minutes late, let's define what is the structure of the inverse doing in the functions. So in a group, we have the inverse, yes? And not anything has an inverse because we have, as you know, you have things, monoids that don't have inverse, like the matrices. Not any matrix has an inverse. So, if we have a map, something like an inverse in the function side, come on, yeah, okay. Then this function translates into the properties of a linear map satisfying this diagram. It's quite weird, but the idea is the linearization of the inverse. Don't worry about this, it's just the linearization of the inverse. And notice that not any bialgebra has this property. For example, the things coming from things that are not groups, maybe they don't have antipole. Yeah. So it's very group thing. They having this map, the antipole. So, last example and pause. What is the difference between having this map, the antipole or not? The same difference of having an inverse or not. So, let's take a subset of matrices that do have inverse. So, let's take, for example, the special linear group. So, this is a group. The group of matrices that has determinant 1. If you multiply two matrices with determinant 1, you get a matrix with determinant 1. So it is a group. The inverse of a matrix with determinant 1 is a matrix with determinant 1. The functions on this group has the following property. These are the polynomials the polynomials in n square variables as any function, any matrix, the functions on any matrix, but we have the property of this set is all the determinants are equal to 1. And we know that determinant can be given by a polynomial, yes? It's a polynomial, I wrote the definition of a determinant using the symmetric group. Yeah, this is a way to write the determinant of a matrix. And if you write the determinant like this, then you see this is a polynomial. And if you put any matrix, if you replace the variables here by the elements of a matrix of determinant 1, the result is always 1. Yes. So the functions on the group are the polynomials, but with this relation that each time we use the determinant, it should give us 1. So the determinant should be itself 1. This is why we divide by this two-sided ideal. Yes, and this is called the algebra of rational functions on this group, and it is a Hopf algebra. because it is a bialgebra and we have the antipole. So I will give you the reason why this is a Hopf algebra with this multiplication, this counit and this antipole in a couple of minutes. Yes? And you will see why the multiplication is given in these terms, okay? But after a break, let's do a break of 10 minutes. Are there any questions so far? Do you have any questions? No? Okay. Yeah, someone there in Zoom? Any questions? No? Okay, let's go back in how many minutes? 8 minutes. So 4 p.m., 10 minutes, we're back, okay? We're going back. So show me your thumbs up if you agree. Okay. You can ask whatever you want in the break, via chat or just asking, okay? You're free to ask. Okay, I will explain the diagram of this one in the Hopf algebra. Yes. I will do it with groups, and then why with the functions is going this thing. So, suppose we have a group, and the rule for the inverse is like this. You take any element, and this element has an inverse. So first, we do the diagonal map. Give me 2 copies of this element. And then you apply the inverse on one side. I forgot to write times G. Here you apply the inverse on one side. And here you apply the inverse on the other side. And then you multiply back. And this should give you the element, the trivial element. Yes? On one side you get G minus 1 times G, which is the unit element. And going from this side you get this one. So you see that here is the multiplication. You see that we are multiplying something and we get the E. But the E is a distinguished element that lives in here. And how do we obtain this element? Okay, the idea is in the middle there's something strange, is we have a map from G to E that is sending each element to E. And then we have the unit here, sending the E to G. Yes? And this map is the trivial map sending any element of G to E is actually in the diagram of Hopf algebras is the dual of the counit. Yes? We have always a map from G, from any group to the group of one element is the one sending any element to the true element. So this is why we have two maps in the middle for the dual version. In the dual version, we have to invert arrows. I think I put the diagram the other way around. Yes. Here is the multiplication. And here is diagonal. Here is the multiplication or the diagonal star. Here is identity tensor antipode. Here is antipode tensor identity. Here is the co-multiplication. Here is the co-multiplication. And going up is antipode unit. Here in the slides is the other way around, but it's the same idea. Yes. Okay, let's resume again what I was talking about. Actually, let's see why do we have this co-multiplication. And the co-multiplication in the functions on the matrices works for any matrix, not for the invertible ones. Yeah? So why do we have this formula? Let's see where this formula comes from. The idea is the co-multiplication is the transpose map or the dual map of the multiplication. So if we want to compute the co-multiplication of a variable in the polynomial ring, we evaluate it in two matrices. Yes? In this way, we will have the answer in terms of the elements. So by definition, our co-multiplication is the transpose of the multiplication. So by definition, this is just the function xij evaluated in the product A times B. Yeah? So this is my definition of our coproduct. And what is the element ij in the product of two matrices? Is the exercise of linear algebra. This is, so let me write A is Aij and B is Bij, okay? The matrices. I will write with capital letters the matrices, with small letters the elements on the matrix, the entries. So, as we know, the Ij element of a product is given by a sum of a multiplication of the elements of a row of A, so you write of the I row of Aik, times the column of B, the J column, like this. This is the very well-known formula. But this guy is our coefficient in the matrix A of the Ik entry. So this is Xik applied to A, the first one. The second one is Xkj applied to B. Yep, J. So, if we have two functions that are the same on any matrix, then voila, we have a formula. We forget the elements and we write the formula. A diagrammatic way to see this is in the book of Christian Castle, very nice. The co-multiplication of this matrix, so suppose we put our variables in a matrix. Yes? So, if we want to do the co-multiplication of each one, so I will write co-multiplication of each one by putting the delta before, is just by doing the same computation as matrix product, but with the tensor. So it's like, it's the diagonal thing, but with this notation, yeah? Voila. So what does it mean? It means that, for example, the coproduct of x1, 1 is first row, first column. But instead of multiplying, we put tensor in the middle. x11, tensor x11 plus x12, tensor x21. So in this way, you don't forget how the thing is, or maybe you remember the formula of the multiplication of matrices. So it's very nice in both ways. What about the coaction? You can do the same with the coaction. The coaction is the dual, the transpose map of the action. So the coaction of any element in a matrix A is just xij of wait. The coaction is it gives us a number, yeah? So it's the dual of the unit. So this is a number. Which number? Is the number given by xij of the unit. Yes? This is in general because we have a unit element in the matrix. So the unit element in the matrix is nothing else than our identity matrix. Yes? So the co-unit in any variable is the entry of the identity matrix. So the entry of the identity matrix is 1 if the entry is in the diagonal and 0 outside. So this is delta ij. So this is why we have the formula, the epsilon is delta ij. And a way to write the formula for the epsilon is we put the epsilon and we should have the identity. Yeah? And for the antipode, is a way to construct the inverse because we do the same computation. So the antipode on xij on a matrix A is the ij entry of the inverse of A. Yeah? This is just the formula. And the formula in the slide is kind of strange because we have to give the ij component of the inverse of the matrix. And you know that you have to apply the adjoint matrix to compute the formula. So this is the, how did I write? The adjoint the ji element of the adjoint matrix of X. So in our example, so we know how to compute inverses. So the antipode on this strange matrix of variables is the inverse of this one. Since we are dealing with the functions on matrices of determinant 1, we don't have to care about the determinant. So it's the inverse of this one. And the inverse of this one is x22 minus x12 minus x21 x1. So in a way, we are putting in formulas all the formulas that we know from linear algebra. How to multiply matrices and how to invert. But in general, with polynomials. Yes? So what we did is, this is the computation for all the coproducts, co-units, and antipodes for any element, as I did here, for the case n equal 2. So 2 by 2 matrices. But of course, it works for any n. And magic, it's not magic. The idea is, you take a group, and then you can compute the functions on the group. Okay, it is a Hopf algebra, has a very rich structure. But we want to go back to groups. I don't like Hopf algebra. Okay, let's take the spectrum. Okay, go back, take the spectrum. And what do we get? The same group. Yes, so very nice. And this is not only working for this example, it works in general. And this is a theorem of Cartier. The picture is of young Cartier. He proved a very, very, very general theorem that actually we are talking about the same things in geometry and algebra. When you take a group, it's the same as taking a commutative Hopf algebra. So the definition might be weird, or say, what is going on with these Hopf algebras? But actually, we are talking about the same things. One is looking at the set as groups. The other one is looking on functions. So we are looking on functions, okay? And this is what we do in physics. We're looking at observable states, things that we can measure. We don't look at particles itself, but at the position, temperature, and things like that. These are functions, yes? So it's a very good way to think about all the things. So Cartier, the theorem of Cartier says that any finally generated commutative Hopf algebra is isomorphic to a function algebra on a group. So if the Hopf algebra is finite dimensional, the group is finite. And moreover, if it's not finite generated by some strange thing, then we erase the affine algebraic group and we put the Prof instead of that. So the theorem is quite general. And so every time you have a group, there is a commutative Hopf algebra somewhere. And on the other way around, every time you have a commutative Hopf algebra, you have a group. So talking about groups or commutative Hopf algebras is the same. In categorical terms, what I showed you is the following tensor equivalence. Yes, this equivalence of categories, not tensor, sorry. It's an equivalence of categories. The categories of affine groups is equivalent to the category of finally generated commutative Hopf algebras. So the way of going from one to another is by first taking the functions, so quotients of polynomial functions, and going back is taking the spectrum. Yeah? So this is a point of view of doing a modern algebraic group theory. And you can see that in the books, in a very well-known book of Hochschild, And this is on algebraic groups. And the other book is from Walter Ferrer and Álvaro Ritatore, where they do a lot of algebraic groups, but when they say take an algebraic group, they're actually taking the Hopf algebra of functions. Why? Because you can do a lot of computations with the algebra and maybe not with the group. The group is maybe too complicated, and then you go to the algebra side and then you compute a lot of things, and then you go back. Yeah? So, up to now we talk about commutativity, but from the very beginning I showed you that we have dual things. Associativity corresponds to co-associativity on functions. The unit corresponds to co-unit on functions. Commutativity on something corresponds to something called co-commutative in a coalgebra. It means that the result of the co-multiplication is the same as if you twist what is given you or not. Yes? The idea is we have the diagram of commutativity, and then come with me to the blackboard. We have the diagram of the commutativity, and then we invert the arrows. Of course, you have to use the flip. So the commutativity for an algebra A was like this. We have two elements, we multiply them, or we twist first, and then we multiply. And then the commutativity is that this should be a commutative diagram. So for the co-commutativity is the other way around. So I will write it in like a mirror thing. No, let's invert the arrows. For a coalgebra, we co-multiply and then we twist. Let's invert the arrows. I said I invert the arrows. Co-multiply, twist is the same as co-multiply. So in Sweetler notation, it means that I wrote there the co-multiplication of one element is the same as if we twist the result. And this is tau composed with delta. So this is something that is co-commutative. Okay, strange thing. But we have a lot of examples. And all the examples, the easiest examples of something are co-commutative. For a coalgebra, to take a group. And with the group, we have the group algebra. Which is the group algebra, for those that you don't know, is you take the elements of the group as they were a part of a basis of a vector space, and then you do formal linear combinations. Let's put lambda. Yeah. I will write it bigger. Of course, these formal linear combinations has to have sense. So all the lambdas have to be 0 almost everywhere. So a finite number. Only for finite. So if the group is finite, everything is there, but if the group is not finite, we have to be careful. Okay? So this is the group algebra, and the group algebra is a Hopf algebra, but just taking the diagonal. So nice, very nice. And of course, if you take the diagonal, if you switch, it's the same. So it is co-commutative. Because you don't see if you are switching the terms. The first terms run with the second. So it is a Hopf algebra, and it is co-commutative. Okay? So the very first examples of Hopf algebras are functions on groups, but also group algebras. So the theory of Hopf algebras contains the theory of groups. And this is a more involved example. I will explain this example very well in the last lecture. It is the universal enveloping algebra of a Lie algebra, and it is also co-commutative. The thing is, when you think about groups, having this co-multiplication means that we are thinking about algebra maps, as I told you before. Groups and functions, when we go back to groups, we think about algebra maps. So anything with this co-multiplication means we have algebra maps. And when we have this kind of co-multiplication, this is not the same as here, means that we have a derivation. Yes? One is algebra maps, and the other one is related to derivation. So you see here, in the second example of a Lie algebra, if we interchange the first and the second tensor of any of this summand, we get the same. So it is again co-commutative. All right? Theorem due to a lot of people. Why? Because it was proved in several steps. And the first version is a version in topology, which is called the mean or move theorem. Yes? But if you translate, as I said before, all the geometry or topology into algebra, then you get this result. Of course, there were some technical issues, and you have to prove it for different things. So this is where it enters in the theory Peter Gabriel, very well known algebraist, Constant, and our hero of today, Cartier. And what is the theorem? The theorem is, if we have a field of characteristics 0 and algebraically closed, if you don't know what is that, don't worry, check the complex number. Suppose you have the complex number and you have a co-commutative Hopf algebra. Then the Hopf algebra is a mix of the examples I gave you before. A universal enveloping algebra of a Lie algebra and a group algebra. Nothing else. Yeah? This is a kind of semi-direct product. And who is the G? The G is the set, the G Lie algebra is the set of elements having this co-multiplication, which I told you means that this is something related to derivation. And the group is given by the group-like elements. The group-like elements are the elements that satisfy that the co-product is likely in the group case. Yes? So, to sum up, let's go back. If we are talking about commutative Hopf algebras, they are nothing more than algebras on algebraic groups or finite groups, okay? Or compact groups. There is also a theorem for compact groups and locally compact functions, like functions on a locally compact space. So this theorem is more or less saying that if you have something that is commutative on functions, the functions that are commutative corresponds to groups, finite, algebraic, and compact. So on the other version of the commutativity is the co-commutativity setting. And the thing is, if you have something that is co-commutative, then it's related to Lie algebras. So commutative groups, co-commutative Lie algebras, and group algebras. So this is what is called the classical setting, because the group theory and Lie theory was developed in the 19th century, and we call it classical, and everything related to geometry has to do with studying action of groups, Lie groups, Lie algebras, and things like that. So, what is commutative and co-commutative comes from group theory or Lie theory. So, more or less, we know that. We know that, maybe not me, but it is known in books and everything like that. We know a lot of things. So what is a quantum group? This is what we are here today. So I presented the classical picture, and now it took me 1 hour and a half to show you why we call quantum group some things. What is our problem? We don't have a definition. So we don't have an axiomatic definition for a quantum group. So, sorry about that. The idea is we study examples. Which examples and why? Okay, what was the idea of today? So you go home, or you stay at home, but you think in lunch or in dinner. Okay, that has to do with geometry and algebra, and there is a dictionary to go from one side to the other. And in the algebra side, we have commutative or co-commutative things, and in geometry, we have groups or the algebra. But what if something is going on that our algebra is not commutative? So, first question, why should we need to study that? Because it appears in nature. When we study particles. In the physics, macro physics, everything is commutative. Newton's thing is more or less commutative. If you study in the space, and you want to when you study astronomy, you look at classical groups, the groups of rotations, translations, or something like that. But if you go into particles, something strange happens. If you want to measure things, they will have a problem. If you measure first in one order, the position and the momentum is not the same if you measure first the momentum and then the position. So, but it's not so bad. So there is a relation between them. So our algebras become non-commutative, but non-commutative. So actually, we can deform our algebras to have our model. Yeah. So we deform the algebra in a way that if we put our deformation parameter equal to 1, then we can go back to our algebra, or to 0. We will see some examples of that. So we deform our algebra and we get a non-commutative algebra. Okay, now my dictionary was, right, take the spectrum, then we get the geometric object. The problem is, the spectrum has nothing to do with the object because it could be trivial, and our object is not trivial. Yes? When we try to do the computations, then we get a problem. When we apply the spectrum, this has nothing to do with groups. So we cannot go back. So once we quantize, or we deform our algebra, we cannot go back to groups. So what should be there is called, a magical word, coined by Drinfeld. It is called a quantum group. So what is a quantum group? In this setting, it doesn't exist. Okay? When we talk about a quantum group, we are talking about a non-commutative Hopf algebra. Yes? There is no geometry there. There should be something. We should have the ideas of geometry, but this is not well defined and we don't know what is going on here. But we keep the ideas. So we do all computations on the algebra side, but keeping the idea that is related to geometry. So we talk about non-commutative geometry. So when you see non-commutative geometry somewhere, in some title, is related to these things. Actually, we are studying non-commutative algebras, Hopf algebras or something related.
So,
yes?
I didn't get the motivation why you need to do the deformation before going back to the...
Yeah, this comes from physics. When you study particles, yeah, small particles, protons or electrons or something, when you want to measure things, it depends on the other when you measure. Why? Because if you want to measure something, you have to look at this something, and if you put a photon on that, then it changes the states. This is the uncertainty principle. Yeah? So if you do in different orders, the result is different. So this is why it is not it's not commutative. Because commutative means no matter the order that you measure, the result should be the same. Yeah? If you throw a ball to the air and you try to compute the speed or the position, it's the same if you compute the speed or the position in any order. But it's not the true with particles. But Planck observed, or maybe another one before him, that the difference between these two things is not so strange. It can be corrected by a constant. And this constant is the Planck constant. This is the origin of the theory. The very mathematical way is you deform the multiplication. You will see that in the next lecture. We deform the multiplication by. Okay? Yeah? Tell me. Okay or? Yeah. We can talk later. You're here. Any question on Zoom? You want to ask something? Or I continue with the idea? Okay, I will answer the two questions after I give the definition because they are very interesting and actually I'm working on them. Not in the first question, in the second. So, Drinfeld, who was the one that introduced the term quantum group, give the definition that a quantum group is the opposite category of Hopf algebras. Because this is related to the picture here. Come on, go back. The picture here that one category is the opposite of the other one because when we go to one side to the other, the arrows are inverted. So Drinfeld defined quantum group, the category quantum group is the opposite category of Hopf algebras. So the definition that Drinfeld gave, I'm going to talk about this in the fourth lecture, is to deform a commutative Hopf algebra to obtain a non-commutative Hopf algebra. So this is not related to the picture I gave you before because we were talking about groups, not the algebra. But it's more or less the same idea. And so we deform something to become non-something. Yeah? For the algebra of functions was commutative, we deform them non-commutative. Now we take enveloping algebras. They are co-commutative, we deform them. They are not concommutative anymore. So, in the folklore, the people talk about what is a Hopf algebra, what is a quantum group in general, is a non-commutative or non-co-commutative Hopf algebra. So, also, the definition is quite general, and there are examples of Hopf algebras that are not quantum groups in some sense, or physical sense, and it's not clear. Yeah? So I have, with my co-authors, we made the following definition. Our definition is that a quantum group is a more specific thing. It's a deformation of an algebraic object. The algebra of functions on a group, or the enveloping algebras of a Lie algebra. And not any algebraic object, not anything, but something related to symmetries. The algebra of functions on a group that the group is giving us the symmetries of something, or the Lie algebra that's giving us the symmetry of something. As maybe if you're studying physics or something related, you know that a lot of problems have symmetries on groups or Lie algebra. So the idea is we deform the things, with the idea that we can get back to our classical things when we put the parameters equal to 0 or to 1. So this is not a real definition for mathematician, because we don't have axioms and we cannot say something is a quantum group or not. The theory has a lot of years, has developed from the 86, and we still don't have an axiomatic definition. And because of that, the theory is based on examples. So I will show you in the lecture 3 and 4 the examples of how we deform the coordinate ring of a group. And this is more related, this is how people do an analysis, do quantum groups, with versions of this object and the completions of this object with respect to some topology. And in the last one, I will introduce these objects, the deformation of universal enveloping algebras. That is more or less the origin of the theory, and has to do with people working in Lie theory and a lot of things in physics and neutrinos, physics of particles, where we have the Heisenberg algebras, the special unitary algebras and things like that, and then quantum harmonic things appear here. The quantum oscillator algebra are this kind of objects. And that's it for all. That is all for today. And I'm open to questions, last minutes, so I will start answering by one in the chat, or you can make one question whenever you want. Now, first in the audience here, do you have any questions? Okay? So, let's go back to the chat. Yes, the first question about Kohn. Kohn was studying, is the intuition and the idea is the same, because Kohn was studying functions on a manifold, a smooth manifold. So we're talking about smooth functions on that manifold, and this is more difficult to explain because one has to be careful because there is a topology and differentiation behind, but it's the same idea. You deform things and you have non-commutative things on the smooth functions on a smooth variable. Yes? And you use different things. You try to use forms and compute things like that, using the differentiability of some things, or try to define differentiability of something. These are well studied, yes, and well, Kohn wrote a lot of things about that. The second question is, yes, quantum supergroups are super interesting. They appear in physics a lot, and they satisfy the same picture, but a super picture, because we have super geometry and super algebras. So if we go to the very first slide, if we put super in every word in the slide, then we can do the same, yes? You can define super geometry with super groups, and of course, when you take the functions, you take the notion, you have the notion of super algebra, and you have the notions of super categories. Everything super means you have a graduation by the group of two elements, set 2. You have even elements and odd elements. So it's not just simply taking two pairs of the same thing. It's different, but we have a dictionary from the super word to the word up back. So if you understand this picture, you can understand the super word, and if you have something super, say, you can bosonize back to our classical word. Classical means by that, okay, no commutative, things like that. But yes, the super theory is very super important. Yes, we have theorems in quantum groups, or maybe, you know, we have theorems in the vector space. I will say the vector space theory that are true for vector spaces, but not true for super vector spaces. I mean, for quantum groups, they are true, but not for super quantum groups. Or, yes, and there's a lot of theorems that we don't still know that they are true. So the theorem of super things is still under development, and we know that a lot of theorems are true when you go from the category of vector spaces to the super one. So some things are true. For example, the theorems I gave you before are true. The theorem of Cartier is true. You have a super commutative Hopf algebra is related to a super group, super algebraic group. And it is known what is a super algebraic group and things like that. But, for example, we have problems with definitions of super Lie algebras. There exist actually super Lie algebras, and the quantum groups related to super Lie algebras can be constructed using more or less the same theory. We can go back, but some theorems are not true in the case of super, because this is weird. This is a thing that is related to number theory. Why? Because in the super thing, things behave like the field is of characteristic 2. This is strange, but it's like this. I don't know why. So some things are true, but some things are not. And yes, we do have. In general, in mathematics, we do algebraic nonsense, and we think about more than super, we call it colored. And in these categories, it happens the same with the super thing. There are theorems that are not true any longer. Or say, some things that are conjectures in the classical case, in the vector space case, we know that they are false in the super case. Yes, so to sum up, the super theory is different. It's a little different. Yes, there's a lot of relations, but it's a little different. So it is interesting by itself. Yes, but the algebra, I'm answering the question about the algebra, the Hopf algebra. Hopf algebras over rings are already studied. So if you change the ring by taking not the field, but a ring or things like that, so the group ring, you obtain a Hopf algebra over a ring. And there's a lot of theory about Hopf algebras over rings. Not all results are known, but we know a lot about that. It is known a lot about that. So yes, ring groups are Hopf algebras over rings. It depends on the ring that you're taking on different results. If you're taking the ring of integer numbers, just integers, you don't get much. But for other rings, I will show you in the last lecture, if you take other rings, then there's a lot of things. Are there any other questions? If not, now you can write me an email. You can look me in internet. You can find my email address there. And it's very easy. If you know, I will try to, no, I don't know. I can write my email here. So you can ask me tomorrow or by email. So that's my email. So you can think about, tomorrow, okay, first question about, I will answer first the second question, not the first one. I will talk tomorrow about Tanaka crime things. So wait for tomorrow for that question. I will tell you that yes, we do Tanaka crime things. Tanaka crime reconstruction things for super groups. So for super quantum groups. Actually, Tanaka crime works for any kind of category that I will show you tomorrow. Yeah? So also it's a way of how the analyst reconstructs things. This was introduced by Voronovich. But yes, and actually a lot of people is doing Tanaka crime thing. And going up. In Cartier theorem, do almost morphisms of Hopf algebras get induced from those of the Lie algebra and group given rise into the Hopf algebra? Yes, you can go back and forth. You have to be careful on which Hopf algebras and which groups are you talking about, okay? So for finite groups, you have finite dimensional Hopf algebra. And affine algebraic groups, finite generated Hopf algebras and so on. Compact groups, on the other side, I think it's called the Kelfand theorem in analysis. Compact groups, and you have functions with compacts or functions or continuous functions on the compact space. This is the theorem. So there are a lot of versions of the same theorem. You have to be careful what do you mean by group or function. And for the Lie algebra, yes, they work exactly in the way that is expected. So very interesting questions. Thank you so much for the questions. Another question, or we'll leave for tomorrow. Thank you very much, Fauci. I think I don't know how to pronounce it. Thank you. See, I hope to see you tomorrow and not less people, yeah? So I'll be motivated. Bye.